Okay, here we're cruising and doing some intergalactic solutions for Chapter 16, problem 1 to 3, so electrostatics. For number 1, you have two opposite point charges separated by 14 centimeters. So here is a negative point charge, here is a positive point charge. Looking specifically 2.5 centimeters away from the negative charge, on which side of the charge is the electric field strongest and weakest? So if that's a circle and it has 2.5 centimeter away from it at any point. Where is the electric field strong? Where is it weak? Well, let's draw the electric field in real quick. We'll do this in do it in green line. So we know electric fields are going positive to negative. Coming in from infinity here because they're going out to infinity here. And then we're kind of get like a big curve like that. Okay. So we're asked, where is this electric field strong and where is it weak? Well, if we just kind of look at charge density here, these are more packed tightly together than these are over here. So over here is going to be our answer. Okay. If we also think about this in a different way, if we think about these electric fields, like if we put a test charge somewhere, if we put a test charge right here, it's being pushed from the positive charge and it's being pulled due to the negative charge. Whereas at some point over here, it's going to be pushed by the positive charge and pulled by the negative charge. And there actually could be a point somewhere out here where this electric field just happens to equal 0. Okay, so that's kind of what's going on here in this kind of scenario. It is going to be some point over here, the 2.5 centimeters on this side is going to be the weakest. At some point over here, there'll be a electric field of 0, which is actually one of the problems that we do. So, and as an example in class. So yeah, there's problem 1. For problem 2, what we have is a point charge, boink, and it feels an electrostatic force of 4 newtons imparted on it. So that is F net equals 4 newtons. By a random number of charges. So we don't know if it's, one charge out here, 2 charge, or a whole plethora of them. Can the force exerted on each of these individual charges be determined from this information? Why or why not? Well, the answer is it cannot. This 4 newtons acting on our point charge to begin with, that is the sum of forces. And we don't even know where these things are distributed. So what we would need to know in order to get any force on one of these particles out here, I'll draw it in pink, to get the force on that particle, we would need to know K, which we do, but then we need to know Q1 and Q2, and we need to know the distance, r squared, between this. We need to know this distance, and we would need to know this distance, and this distance, and this distance, and this distance, and that distance, and this distance, and this distance. We need to know all these r values. We don't know any of this. So while we happen to know the net force in the middle, to get everything else on the outside, we don't have any of that information. In order to actually figure something out like that, we would need to know n minus 1 terms, where n is, we need to know Q1, we need to know some Q values, and then maybe we need the r squareds. So we need a ton of information in order to go solve this. We just can't do it right now. And last but not least, a atom has an excess of 3 electrons. What is the charge on this atom in terms of coulombs? Well, if it's got 3 electrons on it, that is 3 elementary charges, and it's negative because they're electrons. That's why we put the negative there. And that's just 3 times the elementary charge of 1.6 times 10 to the minus 19 coulombs. And whatever that number is, it's about 4.8. Woo! Not too bad. All done. Honestly, in the past, students have just given me this as an answer. I'll take it. I did ask for coulombs, but whatever. I'll take it. That's it. That's the first 3 problems. Nothing too crazy. I'm just asking you to think about some electrons, think about some net forces, and think about electric fields. But with that, we are finished. Sub 5 minutes. Take it easy.